In this video, we're going to derive point and interval predictors of a new response at a given value of the explanatory variable. Here's an overview of our development in this video. We'll first identify the distribution of the response at a given value of the explanatory variable. We'll then have a short discussion on the difference between prediction and estimation. We'll then find a point predictor of a new response at a given value of the explanatory variable. We'll derive the variance and the standard deviation of the difference between the new response and the predicted response. And then we'll find estimators of that variance and standard deviation of the difference. Once we have those, we'll give the formula for the studentized version of the difference and identify its sampling distribution. And once we've identified the sampling distribution of that studentized version, we'll use it to derive interval predictors of a new response at a given value of the explanatory variable. So let's first identify the distribution of the response at a given value of the explanatory variable. Our goal will be to develop point and interval predictions of the value of a new response, which we'll denote by y star, at a given value of the explanatory variable, which we'll denote by x star, from the simple linear regression model given here. Y star equal to beta 0 plus beta 1 times x star plus epsilon. Note that y star is a random variable. Its expected value is beta 0 plus beta 1 times x star, and its variance is equal to sigma squared, which is the variance of the model error term. If the model error term is normally distributed, then y star will be normally distributed as well, and so we can express that this way. Y star, and then tilde for is distributed as, and then as a normal distribution or normal random variable with a mean equal to beta 0 plus beta 1 times x star, and a variance of sigma squared. Now, since the model parameters are unknown, these prediction procedures will necessarily be based on an estimated model consisting of the least squares estimators of the beta parameters, beta 0 hat and beta 1 hat, and the corresponding estimator of the model error variance, sigma hat squared, which have been calculated using a previously obtained sample. Now note that because the model error terms are stochastically independent, and because the model parameters are estimated using previous data, the new response, y star, will be stochastically independent of the previously obtained parameter estimators, beta 0 hat, beta 1 hat, and sigma hat squared. Now let's talk briefly about the difference between prediction and estimation in what we're doing in this lecture video and in the previous. So in a previous section, we developed a procedure for estimating the mean of the distribution of the response when the explanatory variable has a certain value. Note that this mean is constant. Now, estimating a constant is akin to trying to hit a stationary target. In this section, our purpose is to develop a procedure for predicting the value of the response when the explanatory variable has a certain value. Note that this response is not a constant, but a random variable. Now, predicting a random variable is akin to trying to hit not a stationary target, but a moving target. This impacts the relative sizes of interval predictors compared to interval estimators. In order to have the same level of confidence in an interval predictor as in an interval estimator, we will need to cast a wider net to capture the random variable than would be needed to capture a constant. And so for this reason, interval predictors will always be wider than interval estimators at the same level of confidence. Next, let's find a point predictor of a new response at a given value of the explanatory variable. Consider as a point predictor of a new observation, which again is denoted y star, the random variable y hat star, which is obtained by evaluating the estimated model at x star, so that y hat star is equal to beta 0 hat plus beta 1 hat times x star. Now recall that in developing a procedure for estimating the mean of the response when the explanatory variable has a certain value, we chose an estimator which had an expected value that was equal to the response mean, so that the estimator was unbiased. That is, the expected value of our estimator, mu hat sub y given x equal to x star, is equal to the mean that we are trying to estimate, mu sub y given x equal to x star. However, in the present situation, the value we wish to predict, y star, is not a constant but a random variable. Requiring the analogous statement, which would be the expected value of our predictor, y hat star, being equal to y star, doesn't make any sense because the left-hand side, the expected value of y hat star, is a constant, whereas y star, the right-hand side, is a random variable. So we need to base our selection on a slightly different criterion. We do this by comparing the expected value of the estimator and the expected value of the random variable to be predicted. We then try to find a predictor that has an expected value that is equal to the expected value of the random variable to be predicted. This comparison can be made by focusing on the difference between the random variable to be predicted and the predictor, and finding the expected value of that difference. Note that because the least squares estimators, beta 0 hat and beta 1 hat, are unbiased, the expected value of the difference between y star and y hat star is equal to 0. The expected value of the difference y star minus y hat star, by linearity of expectation, is equal to the expected value of y star minus the expected value of y hat star. The expected value of y star is beta 0 plus beta 1 times x star. The expected value of y hat star is equal to the same quantity, beta 0 plus beta 1 times x star. And so their difference is equal to 0. Since the expected value of the difference is 0, the random variables y hat star and y star have the same expected value. And so this makes y hat star a natural predictor of a new response, y star, from this model. Next, let's derive the variance and the standard deviation of the difference between a new response and the predicted response. Now first note that because the new response, y star, is stochastically independent of the least squares estimators, beta 0 hat and beta 1 hat, obtained from previous data, and because y hat star is computed from beta 0 hat and beta 1 hat, the new response, y star, is stochastically independent of its predictor, y hat star. This implies that the covariance of y star and y hat star is 0. Now the difference, y star minus y hat star, is a linear combination of these two random variables, a times y star plus b times y hat star, where the coefficients are a equal to 1 and b equal to -1. The variance of the difference is therefore given by this expression for the variance of a linear combination of random variables. The variance of y star minus y hat star is equal to a squared, or 1 squared, times the variance of y star plus b squared, or -1 squared, times the variance of y hat star plus 2 times a times b, or 2 times 1 times negative 1 times the covariance of y star and y hat star. And because the covariance of those two random variables is 0, this simplifies to the variance of y star plus the variance of y hat star. And so the variance of the difference is equal to sigma squared plus sigma squared times the quantity, 1 over n, plus the square of the difference between x star and x bar divided by s sub xx. And simplifying that a bit further, we can express this as sigma squared times the quantity, 1 plus 1 over n plus the square of the difference between x star and x bar divided by s sub xx. The standard error of the difference between y star and y hat star is the square root of its variance. And so the standard error of y star minus y hat star is equal to the square root of sigma squared times the quantity, 1 plus 1 over n plus the square of the difference, y star minus y bar, divided by s sub xx. Now, using this information, the standardized version of the difference is equal to, by definition, that difference, y star minus y hat star, minus the expected value of the difference, which in this case is 0, divided by the standard error of the difference, y star minus y hat star. And so this is equal to y star minus y hat star divided by the square root of sigma squared times the quantity 1 plus 1 over n times the square of the difference between x star and x bar divided by s sub xx. Now, the standardized version has a standard normal distribution if the model error terms are normally distributed. And so we could write this as the standardized version, z sub y star minus y hat star, having a standard normal distribution. However, the standardized version can't be calculated if the error variance, sigma squared, is unknown, which will be the case in virtually all real-world situations. And so sigma squared will need to be estimated, and then we would need to use the studentized version of the difference instead. So let's find estimators of the variance and standard deviation of the difference y star minus y hat star. An unbiased estimator of the variance of the difference is obtained by replacing sigma squared by its estimator, sigma hat squared, which you'll recall is the mean squared error that we obtained from the ANOVA table for the regression, and we replace sigma squared by sigma hat squared, or MSE, in the expression for the variance of the difference. And so this gives the estimated variance of y star minus y hat star being equal to the MSE times the quantity 1 plus 1 over n plus the square of the difference x star minus x bar over s sub xx. The corresponding estimator of the standard error of the difference is the square root of the estimator of the variance, so that the estimated standard error of y star minus y hat star is equal to the square root of the MSE times the quantity 1 plus 1 over n plus the square of the difference x star minus x bar divided by s sub xx. Now that we have the estimator for the standard error of the difference, we can give the studentized version of the difference, and we can identify its sampling distribution. The studentized version of the difference, which will be denoted using capital T sub y star minus y hat star, is equal to the difference y star minus y hat star minus the expected value of the difference, which again is 0, all that divided by the estimated standard error of the difference y star minus y hat star. And so that is equal to y star minus y hat star divided by the square root of the MSE times the quantity 1 plus 1 over n plus the square of x star minus x bar divided by s sub xx. The studentized version of the difference has student's t-distribution with n minus 2 degrees of freedom. Now that we have that information, we can derive interval predictors of a new response at a given value of the explanatory variable. We'll first derive a lower prediction limit for a y star. We'll then derive an upper prediction limit for y star. And then finally, we'll combine lower and upper prediction limits for y star to get a two-sided prediction interval for y star. Using this information about the sampling distribution of the studentized version of the difference, y star minus y hat star, we see that the probability that the studentized version of the difference being greater than or equal to the negative of the upper alpha percentage point of the t-distribution with n minus 2 degrees of freedom, that probability is equal to 1 minus alpha. Now replacing the notation for the studentized version of the difference by the expression that it's equal to, and then algebraically rearranging things a bit, we get the equivalent probability statement that says that the probability that the new observation, y star, being greater than or equal to the quantity y hat star minus the product of the interval coefficient and the estimated standard error, that probability is equal to 1 minus alpha. This implies that a 1 minus alpha times 100% lower prediction limit for the new observation y star is given by the following expression. Y hat star minus the product of the interval coefficient and the estimated standard error of the difference between y star and y hat star. A similar argument shows that the probability that the studentized version of the difference being less than or equal to the upper alpha percentage point of the t-distribution with n minus 2 degrees of freedom, that probability is also equal to 1 minus alpha. And then replacing the notation for the studentized version with the expression it's equal to, and then algebraically rearranging a bit, we get the equivalent probability statement that y star, the new observation, being less than or equal to the quantity y hat star plus the product of the interval coefficient and the estimated standard error of the difference. That probability is also equal to 1 minus alpha. And so a 1 minus alpha times 100% upper confidence limit for y star is given by y hat star plus the product of the interval coefficient, which is the upper alpha percentage point of the t-distribution with n minus 2 degrees of freedom, with the estimated standard error of the difference between y star and y hat star. Finally, a 1 minus alpha times 100% two-sided prediction interval for the new response y star is obtained by combining 1 minus alpha over 2 times 100% lower and upper prediction limits. This gives the interval y hat star minus plus, and then the product of the interval coefficient, which in this case is the upper alpha over 2 percentage point of the t-distribution with n minus 2 degrees of freedom, with the estimated standard error of the difference between y star and y hat star. Now again, the reason that we divide alpha by 2 when constructing a two-sided prediction interval is that we have to put half of the alpha in the left tail and half of the alpha in the right tail in order to have an overall 1 minus alpha times 100% prediction interval. And so putting all of these results onto a single slide for convenience, we have a 1 minus alpha times 100% lower prediction limit for the new response y star, a 1 minus alpha times 100% upper prediction limit for the new response y star. And then we have a 1 minus alpha times 100% two-sided prediction interval for y star. Now all three of these can be expressed as confidence intervals. The first, a prediction interval based on a 1 minus alpha times 100% lower prediction limit, would be the interval with lower endpoint equal to that lower prediction limit, and then an upper endpoint that is positive infinity. The prediction interval based on a 1 minus alpha times 100% upper prediction limit has as its upper endpoint that upper prediction limit and a lower endpoint of minus infinity. And then finally, the 1 minus alpha times 100% two-sided prediction interval shown here is the same as it was on the previous slide. So that's all I wanted to show you in this lecture video. I'll see you in the next lecture video.